Assalamualaikum and very good morning to Doctor. My name is Nurena Maisara Benci Nordin with measure number AE210028. So I'm going to be presenting my group, which is from Group 9, about our group project, which is called as Steady State Analysis of Power System with Photovoltaic Integration. So what is Steady State Analysis of Power System with Photovoltaic Integration? So you will know about it in detail until at the end of our group project presentation. So my group project consists of 5 people, which is Nur Shafika bin Rusli, our leader. Continue with me, Nur Aina Maisara bin Nordin. Then continue with Nur Ainu Madia, Nur Camilla, and the last one is Abdul Hasif. So I'm going to explain the introduction of our group project. So steady state stability is analysis play a crucial role in assessing the reliable and secure operation of power system, especially with the increasing integration of photovoltaic system. PV integration is the process of integrating solar energy into the current electrical system for the purpose of generating electricity. However, the intermittent nature of solar power and the complex dynamic introduced by PV system pose challenge to steady state stability of power system. So, in order to operate in a balanced and stable manner under typical operating circumstances, a power system must exhibit steady state stability.
Okay, my name is Nur Kimila Binti Abdul Wahid. My metric number is AE210031. For problem statement, typically large-scale power systems are normally composed of interconnected subsystem or a simply control area. The connection between the control area is done by using transmission line. Each area has its own load, therefore the connected load must be equivalent to the transmission line. Power flow or load flow are used to determine the steady state of operation of power system. It also important for planning future expansion of power system. Some issues that can affect the efficiency of electricity are faulty wiring, oxidation, and others. Therefore, to ensure the reliable operation of the power system while maximizing its efficiency and minimize downtime, the potential risk to connected to the load.
Okay, so for the objectives, first, to determine the highest load incremental numbers that can be used before the system fails. Second, to propose power engineering solution aimed at facilitating the integration of renewable energy into the future grid. Third, to understand how the integration of photovoltaic system affects system stability parameters by using MATLAB software. Fourth, to study the system operational state using the iterative cost Seidel method and Newton-Raphson method power flow analysis.
To you about simulation for MATLAB. So the first thing for this coding is we need to do the general program for Newton-Raphson load flow, and then we have to do the bus data type of 330 bus bar, which is we choose the IEE 30 bus system, and then after we enter the value of the data, we need to enter the value of line data, and then we have to do the data arrangement for linear data in the different vector. So after that, we have to do the formation of Y bus metric, and then the next one is we need to do the data arrangement for line data in different vector. Then after that, we have to do the Newton-Raphson load flow, then go to the formation of Jacobian matrix, and formation of we have to do the formation of Jacobian matrix, which have formation. We have to do the formation of J1, J2, J3, and J4. And then after that, we need to do the coding for load flow simulation. Okay, we need to do the load flow solution. And then that's the end of our coding. So the first thing we need to do is we have to run the program, then to check whether there's an error or not. So we have to identify the voltage magnitude in the power flow analysis in IEE 30 bus, whether it's still in the allowable voltage range or not. Then after that, we have to find the value of voltage magnitude when it reach the maximum value of real and reactive power until the system will collapse. And then as you can see, we have to enter the value of P and Q in this coding. So we have to enter the value here. In our group, we are choosing to increase the value of P and Q by 10%. Therefore, after we enter the value of 10.6, we need to increase by 10%. So we need to increase by 10%, which is 11.66. Then for Q is 2.09. After that, we have to run the program. And as you can see, the voltage magnitude is 0.991. Therefore, we need to find the value of voltage magnitude until it collapses to get the maximum value of the P and Q. So I already done the simulation before, and the value that are going to collapse the system is when P is 44.07 watt, and for Q is 7.95 mVol. So and then we run the program. So this is the value of the voltage magnitude before it collapses. I think after we find the value of voltage magnitude when it collapses, we need to increase the value of voltage magnitude back when we already know what is the maximum value of P and Q. So the reason why we need to increase the value of voltage magnitude is to get the ideal value of voltage magnitude per unit, which is the ideal value of voltage magnitude per unit is 1.0. Therefore, as you can see, we the value of our voltage magnitude is 0.694. Therefore, to get the value of 1.0, we need to increase the integrating P slowly. So for our group, we're choosing to increase by 10%. So for 0%, we got the voltage magnitude of 0.694, and then we need to increase by 10, which is we have to increase here, and then we run the program. So for the value when we increase 10%, the value of voltage magnitude is 0.820, and then when we run to 60%. And then as you can see, when we enter the value of 60% at the generating P, we obtain the value of ideal voltage per unit, which is 1.018, which is near to the value of 1.0. And then we decide to take the value. So this is the value of voltage magnitude that ideal when the maximum P is 44.07 megawatt, and the voltage for Q is 7.95 megavar. So that's the result for the simulation part. For the discussion part, I'm going to present about voltage magnitude versus real load power. So you guys know, the real power consumed by a load is directly related to the voltage magnitude at the load bus. According to the power flow equation, the real power consumed by a load is given by the product of the voltage magnitude at the load bus, the load admittance Y, and the cosine of the phase angle between the voltage and the load current. So based on the graph, the initial value of load power of voltage magnitude is 0.995 per unit and start to decrease until it reaches 0.694 per unit before the system is collapsed, and we get the maximum value of real power, which is 44.07 megawatt. Okay, the next one is voltage magnitude versus reactive load power. So as we know, the source energy in AC system known as reactive power is in charge of creating and sustaining the magnetic and electricity field necessary for the flow current. Therefore, we identify that the value of voltage magnitude slowly decreased from 0.995 per unit to 0.694 per unit when the reactive power increased from 1.9 megavar to 7.95 megavar. So the last one is voltage magnitude versus percentage load increment. The relationship between the voltage magnitude and the percentage of load increment in IEE bus 30 is influenced by various factors, including the system operating condition, load characteristic, and the capability of the power system to respond to change in load demand. So based on the graph 3.0, we identify that the voltage magnitude slowly increased from 0.694 per unit to 1.018. When the voltage magnitude start from 0% until 60% of load increment.
So in conclusion, we are able to understand how integration of photovoltaic system affects system stability parameter by using MATLAB software. That's all from us. Thank you.